All right, let's talk about one of the most incredible pieces of biological machinery in the known universe, the human heart. It's this tireless engine that just never, ever stops. And today, we're going to pop the hood and see exactly how it works. I mean, really think about this for a second. Every single day, your heart moves around 2,000 gallons of blood. That's an insane amount of work. So how in the world does this one organ, about the size of your fist, pull off a feat that massive?
Well, the secret isn't just one thing. It's more like a perfectly choreographed performance, and it all boils down to three key players. You've got perfect timing, a set of flawless one-way doors, and this tiny little electrical spark that conducts the whole show.
So, first things first, let's start with the absolute basics. What is the heart's actual job? Its core mission. And where is this thing actually located? Okay, so it's tucked away really safely, right behind your ribs and nestled between your lungs. And its mission is basically a constant two-part delivery service. Job one, it takes all the used, oxygen-poor blood from your body and sips it over to the lungs for a quick refuel. Job two, it grabs that fresh, oxygen-rich blood and pumps it out to every single cell, from your brain to your toes, delivering fuel and hauling away the trash.
Now, to really get how it juggles this two-part mission, it helps to think of the heart like a four-room house. You've got two rooms on the right side and two rooms on the left, and each one has a very specific job.
And this little chart here, it's basically the blueprint of that house. You can see how the two sides have totally separate jobs. The right side, that's the blue-collar side, dealing only with the deoxygenated blood coming back from the body. It comes into a receiving room, the right atrium, and then moves to the main pumping room, the right ventricle. The left side does the exact same thing, but for the fresh, oxygenated blood. This total separation is the absolute key to the heart's incredible efficiency. So, you're probably wondering, how does it keep all this blood from sloshing backward? That's where our one-way doors, the heart valves, come into play. You have two that control flow into the big pumping rooms and two that guard the exits. They are these little marvels of engineering that just open to let blood through, and then snap shut with perfect timing to make sure everything keeps moving forward. No backflow allowed. All right, let's follow the blood on its first big trip. This is the pulmonary loop. It's a short but absolutely vital journey for that deoxygenated blood to get over to the lungs and pick up some fresh oxygen. So here's how it goes. All that used up blood from the body flows into the right atrium. The atrium gives it a little squeeze, pushing it through the tricuspid valve and down into the right ventricle. Then, the right ventricle gives a good solid push, forcing that blood through the pulmonary valve and out to the lungs. It's a simple, elegant, four-step process that happens with every single beat. Okay, the blood went to the lungs. It got its oxygen. Mission accomplished, right? Not even close. Now it has to head back to the heart to start its second, much longer journey, the systemic loop. This is the big one, the trip to supply the entire body. Now, this path looks pretty similar to the right side, but trust me, this side is all about power. The fresh, oxygen-rich blood comes into the left atrium. It gets squeezed through the mitral valve into the left ventricle. And then, with a truly powerful contraction, the left ventricle just blasts that blood through the aortic valve and into the aorta, which is basically the superhighway for blood in your body. And this is where you can really see the difference in their jobs. It's a perfect example of form follows function. The right ventricle, its muscle wall is thinner because, hey, it only has to pump blood right next door to the lungs. It's a short commute. But the left ventricle, it has the monumental task of pumping blood all the way up to your brain and down to your toes. That requires way more force, which is exactly why its wall is so much thicker and stronger. It's a high-pressure pump built for a much tougher job. Now, with all this insane work, the heart muscle itself is burning through a ton of energy. And it can't just steal oxygen and nutrients from the blood that's just passing through its chambers. Nope, it needs its own dedicated fuel supply. And that is the job of the coronary arteries. These are smaller vessels that branch right off the start of the aorta and wrap around the outside of the heart, kind of like a crown. They deliver that fresh, oxygenated blood directly to the heart muscle itself. And why this matters is simple and really important. If one of these gets blocked, a part of the heart vessel gets starved of oxygen, and that's what a heart attack is. So we've covered the plumbing and the fuel lines. But what's the command center? What actually tells the heart when to beat? This, to me, is the coolest part. The tiny, unseen electrical spark that acts as the heart's conductor. It's this perfect, instantaneous chain of command. It all starts in a tiny cluster of cells called the SA node. That's the main pacemaker. It fires off an electrical signal that makes the atria contract first. That signal then hits another node, the AV node, which cleverly pauses for just a split second. Why? To give the ventricles time to fill up with blood. Then the signal zips down the center of the heart and fans out, triggering that massive, coordinated contraction of the ventricles. And get this, when you're just chilling out, that primary pacemaker, the SA node, is firing off about 60 to 80 of these signals every single minute, setting the beat for your entire life. But what if it fails? Well, this is where the design gets truly brilliant. The heart has built-in backup generators. If that main SA node gives out, the AV node can take over as a secondary pacemaker, just at a slightly slower rate. And if that fails, other cells can step in as a final last-ditch backup. It's an incredible fail-safe system designed to keep the engine running no matter what. And how efficient is that electrical signal? This quote just captures it perfectly. The signal makes the ventricles contract from the bottom up, from the apex of the heart, so the blood is literally wrung out and pushed up into the arteries. I mean, it's just like squeezing a tube of toothpaste from the bottom to get every last drop. It is a perfect design for maximum power. So there you have it. You put it all together. The four-room house, the one-way doors, that perfectly timed electrical spark, and you get this incredible, tireless engine. It beats over 100,000 times a day, and you never have to think about it. It's just an absolute marvel of biology. Which really just leaves one last question. What are you doing to power yours?